Hi guys, so let's talk about the last section for chapter 11. Amazing, we made it through chapter 11, which means we've officially finished almost all of our curriculum. We have one more section to go, which is 12.1. We don't really do 12.2 because it's not really tested anymore, and as you will find out this year, it's definitely not going to be tested. This is quite interesting. We're basically done with our curriculum for the year. So, in any case, without rambling too much, let's get into 11.2 part 2, and then we'll finish our last chi-square test. So, and again, I'm going to try and keep this very, very brief because I know that my videos are too long, and there's also videos that are being made by the College Board. So, hopefully I can do something better than they do, but we'll see. So in any case, I just want to go back to the document that I referred to from like 11.1 part 2, I think, and that's distinguishing between chi-square tests. So this is something that students have trouble with. We've done 11.1, which was a chi-square goodness of fit test, which was a single sample. And then we're checking how is a categorical variable distributed across that sample. Basically, does the distribution match a claim, or are the values of the distribution distributed equally across the sample? Okay, so you've got two different options there, really. And then the second test we did was a chi-square test for homogeneity. That's very different. That's many samples, and I added on here or treatments, many samples or treatment groups, basically, was what we said. And we're trying to see if a single categorical variable is distributed uniformly or the same across those treatment groups or different samples. Okay, so chi-square goodness of fit test, one sample, one categorical variable. A chi-square test for homogeneity, many samples, at least two, and a single categorical variable. Today what we're doing is a chi-square test for association or independence, and this is a test to see in one sample, crucial difference there again, in one sample, are two different categorical variables associated, or are they independent from each other? Okay, are they associated or not associated, or is there independence there, or are they dependent on each other? Okay, so do they influence each other? So this is also a very, very powerful thing. Is one variable associated with another? Okay, categorical variable. So this is how you tell the three tests apart. So the test we're doing today is this one, but on your calculator, a chi-square test of association or independence is exactly the same as a test for homogeneity. The mathematics of it is not that different, even though it is a very different test that you're actually conducting. Okay, so I'm not going to go over the calculator tutorial for this. If you know how to do this one, test for homogeneity, then you know how to do the test for association or independence. And I believe I made a video for you about the test for homogeneity on the calculator. So it's the same calculator procedure. Okay, so let's go back to the note sheet then. And we look at this, and it says chi-square test for association or independence. So it says we often gather data from a single random sample, important, and arrange them in a two-way table to see if two categorical variables are associated. Okay, our null hypothesis is that there's no association. All right, or if there's no association, we're also saying, so no association, you can also say the variables are independent of each other. Okay, that's how you state your null hypothesis. And then the alternative hypothesis is that there is an association or they're not independent. And then we move on. Okay, then we can draw conclusions and do our test. So the conditions here, same as for the previous test, chi-square test for homogeneity. Same thing. Data come from a well-designed random sample or randomized experiment. And then if you're sampling, please, some of you made a mistake about this on your chapter 10 test. Don't talk about the 10% condition in an experiment unless there was random sampling. If there's no random sampling, then don't talk about the 10% condition. That means you don't really understand the 10% condition. So 10% when sampling without replacement. And then large counts, all expected counts are at least 5. And again, your calculator can give this to you very quickly in matrix form. Okay? And so, chi-square test for independence. Suppose the conditions are met. You can write your hypotheses this way or this way. And I would follow either the question. If the question says do a test for association, then you state your hypotheses in terms of association. If the test says do a test for independence, then you state your hypotheses in terms of independence. If it doesn't tell you what to do, then you just pick one. Okay? And then you start by finding expected counts. So you have to be given observed counts. And again, how you do this is do the test on your calculator, enter the observed counts into your matrix A, do the test, and then the expected counts will be populated automatically for you in your matrix B. And then you do your do step, and then you do your conclude based on the p-value that you come up with. Okay? So, the null hypothesis is true. The chi-square statistic has approximately a chi-square distribution with these degrees of freedom. Again, I'm pretty sure your calculator gives that to you, but it's number of rows minus 1 times number of columns minus 1. Okay? And then the p-value is the area to the right, and your calculator does all this. All right. Visually, it looks again like this. Chi-square, something like this. Okay? And so you'd have a chi-square statistic you find, and this is the probability, the area to the right of it. All right? So, I mean, that's nothing really big surprising there. If you did the previous section, then this is not really too shocking. The only big thing is, again, please remember, important words here, single random sample, 2 categorical variables. Okay, it is really a different test, but the mathematics feels the same. But really it is a different test that you're doing from test for homogeneity. So example 1 says, study followed a random sample of 8,474 people with normal blood pressure for about 4 years. That's a big, expensive study. All individuals were free of heart disease at the beginning of the study. Each person took the Spielberger Trait Anger Scale test. Congratulations. Which measures how prone a person is to sudden anger. Researchers also recorded whether each individual developed coronary heart disease. This includes who had heart attacks and people who had heart attacks and those who needed medical treatment for heart disease. Here's a two-way table that summarizes the data. So this is observed counts. Okay, so, and again, this is my anger level. That's my first categorical variable. And then heart disease, I guess status, you can say, okay, is the second categorical variable. And this is a single sample, a random sample with 2 categorical variables. This is a test for association. Don't do any other test, okay? And then here are my observed counts. This is what you would put into your matrix in your calculator. All right, so let's proceed. Do the data provide convincing evidence of an association? Again, trying to test if there's an association between these things. Okay, how angry I get, or how suddenly angry I get, I guess, and if I have heart disease or not. Okay, is there association there? And then it says carry out an appropriate test. So this is the problem with chi-square testing. There's 3 different chi-square tests. If they just say carry out the appropriate test, and it's not in the context of a specific test that you're doing the question, you need to look at the study design. Okay, so please remember, single sample, 2 categorical variables. Appropriate test here would be a test for independence or association. Okay, they didn't tell us which test to do, so we get to do whatever we want. So let's say state, we want to perform a significance test of, or a test of, okay, null hypothesis, Two ways. Pick one. No association. They're independent. Let's go with no association. Okay. There is no association between anger level and heart disease. And heart disease in the population of people with normal blood pressure. Okay. Or you can say in the population of people with normal blood pressure, like the ones in the study or something like that. That's what they've been doing in our textbook, but this is, I think, good enough. And then alternative hypothesis, same wording, but you say there is an association. Okay, there is an association between, and I'm not going to write the rest, anger level and heart disease, same wording. Okay, please don't be lazy like me and do that on your test or your AP exam for sure. You got to write all the wording out again. Okay, and then please state your significance level in advance. Okay, we will let our significance level be 0.05. All right, then plan, and we're doing this again, our statement of our test. If all conditions are met, or if conditions are met, we will perform a chi-square test for association. Okay, because I said association here, I gotta say association here. Okay, and then let's check the conditions. So random, and it says the study followed a random sample of 8,474 people. Okay, beautiful. Large sample size, or large counts, I guess. This is still called large counts, isn't it? Large counts. Yeah, large counts. Okay, large counts. In this case, remember, it's large expected counts. Okay, so you have to, at this point, enter the data into your calculator, do the chi-square test, get all the results, and in matrix B will be your expected counts. Okay, and so you say, after that work, the expected counts are all at least 5, but you have to write them down. You have to state them. Okay, so you write them. They are 70, 106, 14, 30, 40, 4, 6, 2, 4, and 6, 18. None of them came close to 5, that's for sure. Okay, so you say the condition is met. The condition is met. All right, and then last one is independence. This is weird. We're doing independence inside of a test of independence. Okay. Any case, independence, and we're saying, wait, this is an experiment. Is it? Is this an experiment? Did I say this is an experiment? Nope. Nope. You follow people. You're following people. Let me erase some of this scratch over here. You're following a random sample. This is not an experiment. You just categorize them. Okay? So this is not an experiment. So independence, we have to check the 10% condition. Okay? So you have to say something like, it seems reasonable to assume that there are 10 times our sample size, which is huge, 8474, which is 84,740 people in the population. People with normal blood pressure, in the population. Okay, and what else? I think that's okay. 10% condition when sampling without replacement, check that. Okay, I think that's okay. I'm not sure if you need to make another statement here. Knowing, yeah, I mean, I would think that people's values of their heart disease and anger level are independent of each other. Okay, so I would also just say maybe people's heart disease and anger level also seem to be likely independent. Okay, it's a random sample. People don't have any relationship to each other necessarily. How would one person's two categorical variables influence another's? Doesn't seem like that's the case. Okay, and then you say do. Conditions are all met, and you say chi-squared equals, and write down your formula. I'm looking at my completed note sheet, and it's wrong. Any case, so you're doing this. The sum of observed minus expected squared over expected. Okay, and you're filling that stuff in. And what this gives you, so again, you go back here. My first observed is 53. 53. My first expected is 69.73, something like that. 69.73 squared over 69.73 plus. Please remember our strategy here. You are not writing all 6 of those things down. Don't have to write all 6 of these things down. Do 1, do 2, and then maybe do the last one. Okay, so 110 minus 106.08 squared over 106.08 plus ellipses plus, and then do the last one, which we said was 606. 606 minus, my expected here was 618.81 squared over 618.81. And if I do all that, I get chi-squared equals, and you can write down the components. I don't think you're going to get penalized for not doing this, but this is technically more your speed as the kind of student that you are. Yeah? Okay, so 265, and then you get your chi-squared value is 16.077. And degrees of freedom should be number of categories minus 1 times number of categories minus 1, right? What did they say? Number of rows, number of columns. Okay, so 2 columns, 3 rows. All right? Oh, sorry, 2 rows, 3 columns. And so that is 2 minus 1 times 3 minus 1, which is in fact 2. Okay? And then do your p-value calculation. Of course, your calculator should have spit all this stuff out. The probability that chi-squared is greater or equal to 16.077 is 0.00032, which is very, very tiny. Okay? So now we have the do part done. Please remember, you need to show all of this stuff. You need to show I would like you to show that, show the chi-squared, show the degrees of freedom, and then show your p-value calculation in terms of a probability statement. So nice. And then do your conclude statement. You say, since the p-value, which is 0.00032, is way less than alpha, which is 0.05, we reject the null hypothesis. Okay, there is sufficient evidence to conclude that there is an association between anger level and heart disease. Okay, between anger level and heart disease in the population of people with normal blood pressure. Of people with normal blood pressure. Okay. Alright. That test, after everything we've done this year, that's not too bad. Okay, that's not too bad. You should be able to crack that out, not worry too much. Okay, so then it says a follow-up analysis reveals that the two cells that contribute the most to the chi-square statistic is low anger chronic heart disease and high anger chronic heart disease. A much smaller number of low anger people developed chronic heart disease than expected, and a much larger number of high anger people. So can we deduce that by just looking at our numbers here? Okay, low anger, our expected was, let me go do this, our expected was 70 and our observed was only 53, quite a difference. And then high anger, the number we were talking about here, which is high anger chronic heart disease, we expected only 14 and we had 27. Okay, basically double of what we expected was observed. So those two, and of course these are the components. These are the components as in these numbers right here. Okay, but the components there are those which indicate clearly that those are the two things we need some follow-up study on. Okay, all right. So for the rest of this, guys, I don't really want to ramble on too much more. I think for the rest of this, if you read this, you should be okay. I've gone over this so many times, it's ridiculous. The AP exam tip just says, if you're on the AP exam, you're doing a chi-square test, which you are not this year. You're taking the test with me, but I don't think you're doing this on the AP exam. If you're having trouble distinguishing these two types, and you don't remember to say, which test am I doing here? Don't name the test then. Okay. Now, I don't know how you're doing that if you don't know how to write your hypotheses either. But if you're not sure which test you're doing, then don't name the test. That's the AP exam tip. I think you're better than that. Don't worry about that. Okay. This is not for you. This is not for you. All right. Then example 2, real quick, says, are men and women equally likely to suffer lingering fear from watching scary movies as children? Lingering fear from watching scary movies as children. Okay, researchers asked a sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The following table breaks down these results by gender. Okay, are men and women equally likely to suffer lingering fear from watching scary movies? So, in other words, the question is there an association between gender and fright symptoms? Okay, that's the question. Is there an association between gender and fright symptoms? Okay. And so here, fortunately, what you want to see if you're a girl or a boy is that this, maybe as a boy you don't want that, or as a male, or whatever, but the p-value was low, so in this little situation you can reject the null hypothesis and you get some conclusion. Okay, so there's the data, observed counts right here. Here are my expected counts from, what's this, Minitab or something that put this out. And then here are the components or contributions. Okay, so it says, assume that the conditions are met, explain why a chi-square test for association and not a chi-square test for homogeneity should be used. And here's the reason. Okay, a sample. All right, a single sample was used. All right, so you say a single sample with two categorical variables was used. That's the answer. Done. Okay? Researchers decided to use the null hypothesis. Gender and ongoing fright symptoms are independent. State the correct alternative hypothesis. Really? This is the question? Alternative hypothesis, gender and ongoing fright symptoms are not independent. Okay. I'm sure if you just wrote dependent, that should also cut it. I'm not sure if that's really taboo. Which cell contributes the most to the chi-square statistic? Okay, that's where you look at the components. So you look here, components, which one? Oh, this one. Okay, this one. So the cell that is male and has lingering fright symptoms. Okay, so you call that male and lingering fright symptoms. Has a components, there we go, good. Has a component of, what was it, 1.833. 1.883. Okay? And chi-square was only 4. There's chi-square. So almost half of the chi-square statistic was made up of this one cell. Okay? And then what was the second question? In what way does the cell differ from what the null hypothesis suggests? So null hypothesis is there's no association. What was the null hypothesis? Here. Independent or no association. But in this case, we're seeing that far fewer observed males reported having lingering fright symptoms than what we expected to see. Okay? So far fewer males reported lingering fright symptoms seven of them than expected, which is, the expected is 11.69. Okay, if the null hypothesis were true. All right. And then it says, interpret the p-value. This was probably the worst question on the chapter 10 test. interpret the p-value was not a successful question. Most people just wrote the conclusion to the hypothesis test. That's not interpreting the p-value. Okay. Now, actually, you can use interpreting the p-value in context as a substitute for the conclusion, but not vice versa in a hypothesis test. Okay. So if someone says interpret the p-value, you got to interpret the p-value. You can't write the conclusion to a hypothesis test. Because that doesn't necessarily mean that you understand the p-value. All right. So, if the null hypothesis is true, or assuming the null hypothesis is true, which means this, context, gender and fright symptoms are independent. Okay, that's the context. The probability of obtaining or of getting a chi-square value as large or larger than, and what was it here? 4.028. 4.028 is, and I mean, okay, I guess I should include this, from a random sample of 117 students is, and I shouldn't put a comma, is, what's the p-value? 0.045. Okay, so again, components of interpreting a p-value. If the null hypothesis is true, stated in context, the probability of getting a test statistic, or if you can state it in terms of what we did in chapter 10, a difference in proportions or a difference in means, that's also okay, as large or larger than the one we got from a random sample of 117 students is this. Okay, so those are your components. And then what conclusion would you draw at significance level 0.01? If alpha is 0.01, we would fail to reject the null hypothesis. Okay, fail to reject the null hypothesis. And we wouldn't have significant evidence to conclude that gender and ongoing fright symptoms are not independent. Okay? They're not independent. Now, you may ask yourself, why is this stuff happening? Maybe the guys are just lying because they want to seem brave or something. Who knows? Okay? So there are reasons for that, and there could be follow-up analysis for that kind of stuff based on the fact that this component is the biggest contributor to the chi-square statistic. Okay? All right, guys, I hope that helps. Yeah, like I said, this strange days. Have a nice day.